Our planet is facing a crisis. Greenhouse gases, primarily carbon dioxide, are warming our atmosphere. This warming leads to rising sea levels, extreme weather events, and disruptions to ecosystems. Direct air capture, or DAC, offers a glimmer of hope. This innovative technology removes carbon dioxide directly from the air. DAC acts like a giant air filter for the planet. It captures the CO2 that has already been emitted. This is crucial because even if we stopped all emissions today, the existing CO2 would continue to warm the planet for centuries. DAC offers a way to address this legacy of emissions. The captured CO2 isn't just waste. It can be stored safely underground, preventing it from re-entering the atmosphere. Alternatively, it can be used in various industries, such as producing synthetic fuels or enhancing plant growth in greenhouses. DAC represents a proactive approach to combating climate change. It complements efforts to reduce emissions and offers a vital tool in our quest for a sustainable future. Direct air capture might sound like science fiction, but the technology is surprisingly straightforward. Giant fans draw air into the DAC system. The air passes through a filter, often made of specialized materials called sorbents. These sorbents act like magnets for CO2, trapping the gas while letting other components of the air pass through. Once the sorbent is saturated with CO2, the system heats up. This heating releases the CO2 in a concentrated form. The purified CO2 is then collected and ready for storage or utilization. Meanwhile, the sorbent cools down and is ready to capture more CO2, repeating the cycle. Different companies employ variations of this basic process. Some use liquid solvents instead of solid sorbents. Others are experimenting with innovative materials and designs to enhance efficiency. The beauty of DAC lies in its simplicity and adaptability. It can be deployed virtually anywhere with access to air and a source of energy. The field of direct air capture is burgeoning with innovation, with several companies leading the charge. Carbon Engineering, recently acquired by Occidental Petroleum, is constructing a massive DAC facility in Texas. This facility, dubbed Stratos, aims to capture a staggering 500,000 metric tons of CO2 annually by 2025. Across the Atlantic, Climeworks is making waves in Iceland. They are developing large-scale DAC projects, harnessing Iceland's abundant geothermal energy to power their operations. Their vision is to build DAC plants that capture millions of tons of CO2 per year. Meanwhile, Deep Sky, a Canadian startup backed by Bill Gates' breakthrough energy catalyst, is focusing on a novel approach. They are developing a modular DAC system that uses waste heat from industrial processes, reducing energy requirements. Their first test site in Alberta is expected to be operational by spring 2025. These companies, along with others like Carbon Capture Inc., are paving the way for a future where DAC becomes a mainstream solution for climate change mitigation. Section 4. Scaling up. Challenges and opportunities. While the potential of direct air capture is enormous, scaling up the technology to capture gigatons of CO2 presents both challenges and opportunities. One of the main challenges is the sheer scale required. To make a significant dent in atmospheric CO2 levels, we need to build thousands of DAC plants worldwide. Another challenge is the energy requirement. DAC is an energy-intensive process, particularly the heating phase. However, companies are exploring ways to reduce energy consumption, such as using renewable energy sources or waste heat from industrial processes. Despite these challenges, the opportunities presented by DAC are too significant to ignore. Governments around the world are recognizing the potential of DAC and are providing funding and incentives to accelerate its development. The US Department of Energy, for example, is investing $3.5 billion in regional DAC hubs. Moreover, the private sector is also stepping up. Companies like Microsoft, Google, and Airbus are investing in DAC projects, recognizing the environmental and economic benefits. As the technology matures and costs decrease, we can expect to see an exponential growth in DAC deployment. Section 5. Environmental impact, a double-edged sword. Direct air capture, while promising, is not without its critics. Some argue that it is a costly distraction from the more pressing need to reduce greenhouse gas emissions in the first place. They contend that focusing on DAC could create a moral hazard, allowing polluters to continue emitting CO2 with the false assurance that it can be removed later. Another concern is the land use associated with large-scale DAC deployment. Building thousands of DAC plants would require significant land resources, potentially competing with other land uses such as agriculture or conservation. However, proponents of DAC argue that it is not an either-or proposition. They view DAC as a complementary solution to emissions reduction, addressing the legacy emissions that will continue to warm the planet even if we achieve net zero emissions. Furthermore, advancements in DAC technology are focusing on reducing its environmental footprint. Companies are developing more energy-efficient processes and exploring the use of renewable energy sources. Ultimately, the environmental impact of DAC will depend on how it is implemented and integrated into a broader climate change mitigation strategy. Section 6. The price of progress. Cost and funding of DAC. The cost of direct air capture has been a significant barrier to its widespread adoption. Capturing 1 metric ton of CO2 using DAC can cost $600 to $1,000. However, as the technology matures, costs are expected to decrease significantly. Government funding and private investment are crucial in driving down costs. As costs decline, DAC will become more attractive for climate goals. Section 7. A brighter future. The potential of DAC technology. The future of direct air capture technology is brimming with potential. As research and development efforts intensify, we can expect to see significant advancements in DAC efficiency, cost-effectiveness, and scalability. One promising area of research is the development of new sorbent materials. Scientists are exploring materials that can capture CO2 more efficiently and at lower temperatures, reducing the energy requirements of the process. Another area of focus is the integration of DAC with other technologies. For example, researchers are exploring ways to combine DAC with renewable energy sources such as solar or wind power, making the process carbon neutral or even carbon negative. As DAC technology continues to evolve, it has the potential to play a transformative role in our fight against climate change. It offers a way to remove legacy emissions, achieve negative emissions, and ultimately stabilize our planet's climate. The journey towards a sustainable future will require a multifaceted approach, and direct air capture will undoubtedly play a crucial role. By investing in research, development, and deployment, we can unlock the full potential of this game-changing technology and create a cleaner, healthier planet for generations to come.